All right, so welcome everybody to Hoon School Live Lesson 6. This is going to be the last lesson where we have these big, new, and important concepts. And once you're done with this one, the rest of the course is going to be smooth sailing for you. So in this lesson, we'll continue to learn about cores and what we can do with them. All right, so recall that in last lesson, we started with making a core like this, right? And it has a sample like this, tisfas n0. And this code right here is going to produce a structure that looks like this, right? So here's the whole core. On the left in the battery, there's a single arm, which contains GTH n10. On the right is the payload of the core. At the head of the payload is a sample, this n equals 0. And then if you run this in the dojo, it's going to grab the rest of the dojo subject, and that's going to be the context, right? So hopefully this is all familiar from last lesson. So once we have this, then we set this core as a subject, and then we perform some operations on it, right? So what are we doing here? We're saying we use sendTis to grab dot. Dot refers to the subject. We set this as a subject here. So it says grab this whole core. In this, make a new core where n is changed to 11, and then run the buck arm of that new core. So if we take this code and we run it, like so, it's going to return send.y because we replaced n equals 0 with n equals 11. Then we ran this arm and it says, yes, 11 is bigger than 10. Right. And I'll put this code in the chat. Oops. So then we changed the core to a door, right? So instead of having this bar sen and pinning the sample to the head, we just defined it like this, right, with this bar cap. And we learned in last lesson that these are equivalent, right? This is just two ways of writing the same thing. So we can do the same operation on the door, right? You can say, take this door, create a new one where n is set to 11, and then run its buck arm. And the same thing, we get a yes, because 11 is bigger than 10, right? So finally, we replace this double operation of calling senhep and changing n to 11 and then running the arm with just a single operation, which is using sensig, right? And that just does the same thing condensed into one operation. It says, take this core, change the sample to 11, and then run the buck arm. So as I mentioned in last lesson, this looks a lot like a function where we can replace a value and evaluate it with whatever value you like, right? So in Hoon, these are what are called gates. And so far, we're familiar with that term, right? We have been using a lot of gates like add or mul or GTH and so on, right? But we haven't so far learned what they are inside, how they work inside. And that's what we'll do in this lesson. So a gate is actually very simple. It's just a door with a single arm buck. So, but instead of writing out the door and the arm, we can just use this rune called bar_tis. And so here are two ways we could have written the GTH10 gate. So here's with the gate notation, you have bar_tis, you have the sample, and then you just say what it's supposed to do, right? And here we actually wrote out that there's one arm named buck with GTH n10, whereas it's hidden over here, right? So these are the same thing. And to show you that they're the same thing, we can pin this gate to the face GTH10, and then use sensig to call its buck arm with the new sample value 11. And that gives us a yes, because this gate is just a door inside. So we can do the exact same operation, right? But we can do something that's even shorter and that's perfectly exactly equivalent, which is just call it as a gate with the senhep room. And so here we call this gate GTH10. We use the senhep room that we used before. We say call GTH10 and make the sample 11, and we get a yes. So this syntax right here actually just reduces to this syntax. Senhep is just sugar over sensig on the buck arm of a door. But usually we don't think about that, and we just use it as a senhep. And to make this even clearer, we can even use senhep, this gate calling notation, on something that's written as a door. So here we wrote GTH10 as a door again, right? We have a single buck arm, and we're using this senhep on it, and it just works and does the same thing. So in general, the Bartiz rune works like this. It takes two children. So the first child is some sample specification, like n equals pat ud, or like a cell of 2 pat uds, whatever. But this is in structure mode, right? This is not in value mode. And the second is a Hoon expression. So that's just going to be whatever goes in the buck arm of your door, right? Is defining a sample equivalent to defining input parameters to a function in other languages? Yes. But in Hoon, the sample already has a value and you're swapping the value out. So it's not something that like is, like you can run a gate without any input because it already has something there. So that's kind of different from other languages. So to tie all this together, here are 3 equivalent ways we could have written our GTH10, right? So here's like the most general, like expansive way to write it as a core, right? So first we pin n to the bunt of pat ud. Remember, the bunt is the default value of pat ud, so that's just 0. And then we write a core, right? Bar sen, a single arm called buck, calculate GTH10. Here we write it as a door, so we get rid of this and we just write a sample specification here. And it's the same thing, you still got one arm and it says GTH10. And finally, we can write this whole thing as a gate. So just get rid of this. It's hidden, it's still there, but it's hidden. And you just write it this in the most short and simple way. So is that clear to everyone? Are there any questions? All right, so now that we know what gates are underneath, we can investigate some gates in the standard library and check out what they have in there. So now we know a gate is just a core with a sample at the head of the payload and a single buck arm, right? So let's investigate add. When you type add, this refers to an arm in a core of the standard library. That arm contains a gate. So when you call add, that gate gets pulled out and built right there. After you build it, you can access its various parts like this. So add is a core, gates are cores, right? Cores have a battery and a payload. At the head of the payload, it has a sample, right? So let's try this. So let's build add and grab its lust2 address. And we get this knock formula. And we don't have to worry about what this knock formula means, but just know that this is the uncomputed knock for adding 2 numbers. We can also get the sample for it, so the default value for add. So let's get the lust6 address of add. And we see that it has a default value of a equals 0 and b equals 0. You can use the lust7 address to grab the context, which is going to be the dojo subject that it was built against, since we're running this in the dojo, right? So here it's summarizing the dojo subject. Basically, it's saying there's a core with 33 arms, a core with 1 arm, and this SEM 139 is actually the Hoon version. So, and we can call. So add has a buck arm, right? Add is a core with a single arm buck, and we can call that arm, and the arm already has some values it can refer to, and so it already has some numbers it can add. And so calling it adds 0 plus 0 equals 0, just like that. And since it's a core, you can use sentis to modify its sample and then call its buck arm again. So here we're setting add as a subject. We're saying take that core on the subject, which is add, change its A to 10, change its B to 5, and then run its buck arm. And then we get 15. So, and we can use sensei to do the same thing because it's a door, right? So we can do this a little shorter with set add as a subject, call sensei on the buck arm of add with the sample of 10, 5, and it gives you 15. So the whole point of this is just to show you what a gate is underneath. It's a core, it's a door, it's a structure just like all these other structures we've been working with and studying. So yeah, any questions on that?
Yeah, can you explain again the +2, +6, +7? Like, do you know that already, or was that something like output into the dojo?
Yeah, so any core is going to have this standard structure. So if a core is at address +1, like, and remember back to lesson 1 where you learned about binary tree addressing, right? So if a core is a whole tree is at address 1, then in its left branch, it's going to be address 2. And we know a core always has its battery, its uncomputed arms in address 2. So we always know that going to address 2 of a core can give you the battery, right? We always know that address 3 of a core is going to contain the payload or its data stored as data, right? And we also know that in the left of the payload is going to be a sample, if there's a sample, and the right of the payload is going to be all the rest of the data context. So, and those two correspond to 6 and 7, because you go 1, 2, 3, 4, 5, 6, 7, if you're numbering the binary tree. Does that make sense? Cool, awesome. All right, yeah, any other questions on that? Cool. So suppose that you have a gate and you want to store it for later use so that other programs can call on it or that you can call on it from the dojo. This is what's called a generator. Let's walk through creating and using a generator. So you might be familiar with this from the earlier lesson, but first you have to bar mount the base desk or any desk, but let's use the base desk. So we run this command in the dojo, and what that does is that makes the files and folders on Mars appear on Earth, right? So we do that, and then we see this base folder, and it has all this stuff in it, right? So next, what are we going to do? So next, we're going to open up a new text file in our IDE. And then let's put some code for a gate into our text file, like this GTH10, right? Then we can save this. And the folder we're supposed to save it is Zod, if you're using a fake Zod, base, then the gen folder is for generators. And then we can save it as whatever we like, .hoon. So let's call this GTH10 .hoon. So we save that. Now let's go back to Mars. We run bar commit send base. This takes the changes that were on Earth and pushes them to Mars, right? So we see that we added this file gth10. And now we can run it from the dojo. gth10.9, no. gth10.11, yes. And note that there's only one space here, not two spaces. If you want to edit this generator, then you just edit it and save the file, and then commit again, commit base again, and now you can run it with the new values. And if you have a generator with more than one argument, like you might have a generator that starts like this, right? Your sample is a triple of A is a pat UD, B equals pat RS, and C equals pat T. Then the way you'd call this is as a single noun. So you would call it like this. So you just pass in the whole triple as a single thing. Any questions on that? Why do you call mount and commit with bar, but the generator with less? I think that's a good question. So I think bar is for system related commands. And that's just like, this is how they decided. Like you can make, you can, I'm pretty sure you can make a like mount.Hoon as a generator and then run it with less mount. So I guess it helps with there not being like namespace collisions and stuff. So yeah, it's just convention. Their system commands are with the bar, and like calling a generator is with the less. All right, any other questions? All right. So let's close this. So let's recall that since a gate is a door, right? And a door gives a sample with a default value. It gives whatever type you pass in its default value as a sample, right? There are some reasons why you might want to create a gate with a different default value instead of just the bunt of it, right? So let's give an example where this is going to be useful actually. So recall that we learned about role, right? Role is a library gate for working with lists. It goes over a list and pairwise applies the gates to the entries and reduces it to a result, right? So like, for example, here we have role list pat UD of 1, 2, 3, 4 mole. What this is going to do is multiply 1 by 2, multiply that by 3, multiply that by 4. It gives you 24, right? Because 4 times 3 is 12, times 2 is 24, times 1 is 24, right? So we also learned about floating point numbers, right? And that mol col rs is a gate to multiply two floating point numbers. So you have mol col rs 1.234, 5.678. It gives you that, right? So you think this should work. Here we're trying to roll mol rs over this list of floating points, right? But what actually happens when we do this? It returns 0. It's kind of strange, right? Why does it return 0? So let's investigate this. Let's pull mol rs and check what its default value is. Remember that if we build this as a core, right, we can go to its lust6 address and see what the sample is for mol rs. And it turns out the default sample for mol rs is A is 0 and B is 0. And how roll works is it actually starts by first multiplying the first value by the default value, by the sample here. So what it does is it's going to multiply 1.234 by 0. And that gives you 0, right? and then it multiplies 0 by 5.678, which gives you 0, and then it multiplies 0 by 2.222, and so the whole output is 0. So how can we fix this? We can use this rune called bar col. So it works like this. So the first child of bar col, so this is similar to bar tis, right? But it's a little different. The first child is going to be a Hoon expression, which reduces to a value. And the second child is going to be a Hoon expression, which is going to go in the buck arm of a door, right? So this is like a gate, except this is different. That's the only thing. And what it does is it infers the type of this one. So it tries to tell what the type is, sets the value of this as a sample, and then says the gate has to take that type. A question is, wouldn't having ones make more sense in the sample of mol RS? Yes, actually, I was recently proposing that we should just change that, but for now, it's a useful example. So, but yes, in general, that's a good point. So we're going to use this bar col to fix this. And we're going to make a new gate with it, right? So let's look at this code. So we're going to call something new mol RS and use this bar col. We're going to say the sample of it is going to be 1 and 1, 2 floating point numbers, which are 1 and 1. And then it's going to call the original mol RS on those numbers. So if I press enter here, this is a core, right? So it's going to return. Oh, wait, oh no, because I have this tisfest here. So if I just return new mol RS, that's going to return the core, right? But we can use this to roll over these numbers, and it should work now. So and now it works, multiplies all the numbers. So we define new mol RS as this thing, and then we used it in rolling here. All right, any questions on that? Cool. So recall that before in last lesson, we could have cores where an arm of the core contains the code for another core, right? And of course, this means we can have gates in the arms of cores as well, since gates are cores, right? So here we have a core, and it has 3 arms. The arm double contains a gate, which takes a number and multiplies it by 2. The arm triple contains a gate, which takes a number and multiplies it by 3. And quadruple does what you expect, right? And we can compose this core with a call to triple, which just returns this gate, which is a core, right? So if we return triple, has this output, which is a core, right? But we can also compose it with a call to triple, send have triple on 4. So we're composing this to pulling triple and using it as a gate on 4, and we get 12, right? Because we pulled this out as a gate, we called it on 4 and got 12. Right? So this outer core doesn't just have to be a core, it can also be a door. And furthermore, we can use the inputs to that door in the definitions of these inner gates. So this is called a gate building door. And you can use this to construct a general family of gates all at once. So for example, we're hopefully all familiar with linear equations like y equals ax plus b, right? A denotes the slope of the line, and b denotes where the line crosses with the y-axis, right? And by changing A and B, you can get all sorts of different lines, right? So let's build a door which can produce any linear equation like this as a gate. So here's the code. Let's go over all the parts of this code in detail. I put the code in the chat. So first, you have a door on the outside. That door has a sample, which is a cell of A is a pat UD and B is a pat UD, right? That door has a single arm buck. And here's the definition of the buck arm, which is a gate. That gate has a sample, which is just X, which is a pat UD, and it uses it in its definition, right? That gate also uses A and B, which are passed to it from the outer door, right? And it takes all those and it computes AX plus B. So let's call this linear and pin it to the head of the subject, and then call that door with a sample. So what's going on here? So say linear is this door. We're going to call the buck arm of linear with 4, 2 as a sample. And so what's this going to give us? This is not going to give us a number, right? This is going to give us a gate, right? So if we press enter here, we get a gate. And so it's kind of hard to see what this gate is, but it is the gate which represents y equals 4x plus 2. We could have also written it in sugar syntax like this, right? The sugar syntax here, which we should recall. I'll post that in the chat. So to prove it to you, we can call the gate that was built like this, right? So here we have this builds the gate, and this whole expression calls the gate y equals 4x plus 2 with the input 1. So 4 times 1 is 4 plus 2 is 6. So this gives us 6. So any questions on that? All right. So we're at the beginning. If there's no more questions on that, we're going to move on to the next half of this lesson, which is going to be about recursion in Hoon. So before we learn about recursion, there's a neat trick that we should learn about the runes centis. So far we've used centis as its first argument is a core, right? So we have this core, and then we say centis this core and change its value n to 11. And what that does is that produces a new core, right? But something else we can do is if this first argument is an arm, not a core, but an arm in a core, what centis will do is it'll produce this core with a value changed and then immediately run that arm. So I'll show you an example. So so what we did was, oops. So we took this core, we used centis on its buck arm, and we changed n to 11. And that immediately just ran the arm and gave us yes, since 11 is bigger than 10. And if we had the same code, but just with the core, then, so if we just change this buck to dot, oops. This, oh, there we are. We change the buck to dot, then it returns the whole core, right? So that's a new usage of incentives. All right. So recall that in lesson 0, we studied a simple recursive function like this, right? So this function says it takes an input n. If n equals 0, return n. Otherwise, return the function of n minus 1, right? So if we give this 3, 3 isn't equal to 0. So we go here, return function of 2. Function of 2, 2 doesn't equal to 0. So go here, return function of 1. 1 doesn't equal 0. So go here, return function of 0. And function of 0 says if 0 equals 0, then return 0. So this function returns 0 for any positive whole number, right? Let's understand how to code this function in Hoon. So it's going to look like this, and let's go through it slowly and understand all of its parts. So what's going on here? First, we pin n to 3, and this becomes a sample of a 4, right? We've seen this before. Next, we're going to declare a core with \send, right? Next, that core has a single arm buck, and that buck arm contains all the rest of this code. And here's the definition of the arm, right? So it has some logic. This WHAT says if the first child of the WHAT, which is this, produces send.y, then do the second child. Otherwise, do the third child, right? This first child of the WHAT is a sugar form of .tis. And remember, .tis compares two values, and it produces send.y if they're equal and send.n if they're not, right? So this is saying, is n equal to 0? If so, send.y, otherwise send.n, right? This is the second child of the WHAT. We only do this if this returns send.y, and then this says return n. And this is the third child of it, right? So what's going on here? This sentence calls the buck arm. So first of this right here. And recall what this says is build this core and then run this arm with the changes made, right? So this says build the core and run the buck arm and change to n minus 1. Is using bucks some kind of convention? Yes, it's a convention for when your core only has one arm. But for example, when you write a gate, like with bar_tis, you can refer to a buck arm in there, even though there's not explicitly defined. So it's a convention that's also part of the system. So this piece of code is a core, right? So if we take this core and just type it in the dojo and press enter, it just returns a core, right? It doesn't do anything. It just returns the core. But what happens if we compose this core with a call to its buck arm? So let's take that core and run its buck arm. And it returns 0, right? So this did exactly what our pseudocode function did, right? It took that 3, decreased it, and it returns 0. Right. So what exactly happened? Let's go through it for the sake of comprehension. So n starts as 3, right? Said is 3 equal to 0? No. So we skip this branch and go to this branch. That branch says, build this core and run the buck arm with n set to n minus 1. So n set to 2. Here we are again, but with n equals 2, right? We go here, is 2 equal to 0? No. So we skip this branch and go to this branch, build the score, and run the buck arm with n set to n minus 1. Here we are again with n equals 1. Is 1 equal to 0? No. So build the core and run the buck arm with n equals n minus 1 equals 0. Here we are again, 0 equals 0, yes. So we take this branch and just return n. Any questions on that? So if you have a core with a single arm buck, this is a very common pattern, right? That's actually called a trap. And there's a rune you can use to simplify writing it. And the rune is bar dot. Excuse the typo there. Would ket n give you the previous value of n inside the arm? That's a good question. That's a wonderful question. Let's try this. So let's take our code and change the final output to ket n. So I'm gonna paste it there. And it says find dot ket n. So I guess not. I wish I had a better answer for you as to why, but yeah. Maybe I'll follow up on that later. That's a good question. All right. So if we have a core with just a single buck arm, we can write it more succinctly with this bar dot, right? It just creates a core and puts this child as a single buck arm of it. So we could have written the above equivalently. Instead of sen hep or bar sen less buck and all this, we could have just written it with this, right? Now let's run it. Run this code to make sure it does the same thing. And it gives us 0, right? So if we have a core with a single arm buck, and we just immediately call and run that arm, then we can even write it even more shortly with this rune bar hep. This is called building a trap and kicking it. So this is the rune you actually use the most often for doing recursion in Hoon. So bar hep just takes one child. It puts that child as the single buck arm of a core and just immediately runs that arm. So that means this code here, instead of all this, composing the core with a call to the buck arm, we just write like this, and it does the same thing. So let's try that. And it gives us 0, right? So what would happen if we put this n equals 3, or this declaration of n to the value 3 inside the trap? What would happen there? You might think like, this might cause an infinite loop, right? Because every time we come back here, n gets reset to 3. But actually something different happens. So let's run this code. So it didn't go infinitely. It says tac.n find.n. So what's up with that? So that didn't happen. There was no infinite loop. So what actually happened is, and I wrote the code equivalently 2 ways here, right? So this is the shortest way with this bar hep we just learned. And this is the code expanded out, right? So we expanded this out to a core with a single buck arm. And then we expanded that out to composing the core with calling its buck arm, right? But this code and this code are the same thing, equivalent. And what the sentence does, it says, let's go to this buck arm, rebuild the whole core, and with its wing n change to n-1, and then run this arm, right? But n is defined in an arm of the core. And n is defined in here, and arms are unbuilt code, right? We kind of saw this on last homework. So actually, the problem is here, it says, where's n? N doesn't exist in this core yet. And to make this clearer, here's the two different positions of this TISFAS N3, right? So here it's inside the core, which means it's inside this buck arm, and TISFAS N3 is here, and here it's outside, and that means when we created this core, it was put into the payload, and it's here. And here, CentIS can't find this because it's here, it's unbuilt code, whereas here it found it in the payload. So that's actually why we get an error here. It doesn't go infinitely, it just says I can't find n. No. So when you're doing recursion, you should be careful to put these declarations that you need to use in your loop outside of the loop. That's really the main message here. Can you assign n to a bunt and then add another TISFAS with a value for n? Yeah, I think that should work. Let's try it. So let's take this code and change it. Huh. Oh, well, that was working, but it's running forever. Oh, now, huh? Interesting. Now it's infinite looping. And I don't know exactly why it's infinite loop, but maybe we can figure that out later. So this code is infinite looping. That's a nice puzzle for us. Yeah, maybe this time it keeps setting n to 3. Because maybe this time it can, right, because this time it can find n, so it changes n to sub n1, and so it doesn't get this error inside the CentIS, but then it keeps getting set to 3. Yeah, so nice, very, very perceptive of you. Good job. Yeah. All right. Yeah, great example. All right. So that's a really simple example of a trap, right? We kind of exhaustively looked at it. So for the final part of the class, let's learn to use traps for some useful things and look at some more complex examples, right? So here's something we can do. We can use a trap to say, given an input number, add up all the numbers from 1 to that number, right? So what are we going to do? We're going to set our number to 5 and set our total to 0. And then we have this trap, right? So we go into it and we say, is the number equal to 0? No. So we don't go to this branch, then we go to this branch, right? We take the third child. And this third child says, let's rebuild this core right here and run its buck arm with num changed to num-1 and the total changed to the total plus the number. So here we are again at the hidden buck arm. Remember, this bar have, it abstracts away the buck arm, right? But now num is equal to 4 and total is equal to 5, right? Is 4 equal to 0? No. So we go here. We're saying build this core again, run its buck arm with num equal to 4 minus 1 equals 3. Total is equal to 5 plus 4 equals 9. And then we just keep going, right? So if we run this code, it gives us 15 because 15 is 5 plus 4 plus 3 plus 2 plus 1. Right. We can also, if we don't want to hard code this num here, we can put this trap inside of a gate, right? So here's what we can do. This says this is a gate which takes an input as a num, and then inside of it is this trap logic. So if we press enter here, it's going to return a core, right? Because a gate is a core. But what we can do is we can say, call this add nums gates, and then copy paste this, and then say add nums gates 5. Oh, I forgot to. One moment. Right. So we set this gate containing the trap to add nums gate, and then we called it on 5, right? And recall that we just learned how to save a file, a gate as a generator, and then call it from the dojo, right? So we can even just take this, gate and open up our IDE. So let's take this and save it as Zod base gen add nums.hoon. And then we can do bar commit base plus add nums 5. We get 15, right? We just took that and we saved it as a file, and we committed it and we run it. There's something interesting we can do to further simplify this code. So recall that a gate is a core with a sample and a single buck arm, right? And a trap is also a core with a single buck arm. So there's actually some redundancy here. There's some redundancy here, right? This is a core with a single arm. This is a core with a single arm. So we can just actually recurse into this bar-tis instead of having this extra bar head. So what we do is we get rid of this. We make sure this total declaration is outside of the gates. So we got to move it up here. And then this, we can do the same thing, but this just pings back here every time instead of pinging here. And we can test this code. We'll add nums gates to be this, and then add nums gates 4. You get 10, right? So we change this code. We got rid of the bar hep inside. This recursion just keeps pointing at this instead, and that's totally fine. Any questions on that? All right, so for our last example, let's do one more thing with traps. So it's really common to use recursion to work over lists. So let's make a trap to add up all the numbers in a list of numbers. So here's the code. Is there something a trap can do then a gate can't? Well, so a trap is a core with a single buck arm, and a gate is a core with a single buck arm and a sample. So you can just add a sample to a trap, and then it's a gate. You just wrote a gate a different way because they're all cores underneath, right? So to say it again, a gate is a core with a single buck arm and a sample. A trap is a gate with a single buck arm, and you can just add a sample to it, right? You can just pin something up there. So you can do everything with a gate with a trap, because they reduce to the same structure underneath. All right, so here we have this code. We're working with a list now in a trap. And we're going to take a list of numbers and add up all the numbers in the list. All right. So we initialize numList to be a list of PAUDs 50, 100, 2, 3, 49. And we initialize total to 0. Here we have this bar hep, which is a trap, right? But it's a arm buck, and we immediately run the buck arm, right? So there's no buck here, but it's hidden. This says this what null, recall we worked with this before. It says if numList is null, if it's just a sig, then do the second child, otherwise do the third child. In this case, numList is 50, 100, 2, 3, 49 sig, right? So it's not null. So we go to this third child. That third child says rebuild this core and then run its buck arm with new values for numList and total, right? So because we have this one null here, saying if numList is null, do this, otherwise we're in this branch, we prove to the compiler that numList is not null. Remember, we had an example of this, right, in lesson 3, or lesson 4. And because of that, we can use these spaces i.numList and t.numList, right? So, and if you recall, i.numList is the head of it, so that's just going to be the value 50, and that means we're changing total to be the original value of total plus 50, right? So total is going to be 50. And t.numList is the tail of it, which is the list 100, 2, 3, 49. That means we're changing numList to be the tail of itself, which is just the list with the head chopped off, right? And that means when we go back here again at the hidden buck arm, now we have total equals 50, numList is the rest of this list, and then we just keep going and keep adding up total and reducing this until it's just sig. Then this returns yes, and then we return total, right? So let's run the code and make sure it does what we said it does. And it returns 204 because, well, maybe you can do the math in your head, but all these numbers added up are 204. So, and of course we can put this code into a gate, right? And make it take any input we want, just same as what we just did, right? So here we put the trap in a gate. It takes the gate takes any numList. We call the gate add numList gate, and here we call it on this input, and then it adds those up for us, right? And we could have also got rid of that inner bar hep as well. So instead of having this extra bar hep, we just get rid of it, move this total outside, and we can just recurse into this gate. So no bar hep here, does the same thing. And finally, of course, we can save this whole thing as a file. Save it as add nums list.hoon. Run var commit base, and then do add nums list. 1, 2, 3, 4, 5, 100, 199, whatever. And generator build fill. Oh, here. Yes, thank you. Good eye. There we go. All right. Cool. So we've finished the lesson. Are there any questions on anything at this point? All right, so I will drop the anonymous feedback in the chat. If there's no questions on anything, I can stop the recording, but I will be at office hours in 15 minutes. Feel free to ask me about.
Actually,
yeah,
I have a quick question. Just can you give do you know what we're covering next week?
Yeah, so next week we're going to just look at the standard library, poke around in our Urbit ships, and just kind of try to learn what are some other things we can do. We can learn about maps and sets in Hoon. But the next week and next week are going to be lower intensity lessons. We're coasting from here. We got to like the meat of Hoon, and next 2 weeks will be like just learning more about how to develop programs and like understanding the structure of a system and all that. So yeah.
So ecosystem.
Sorry.
So looking at the standard libraries and the tools that are already there for us, not to reinvent the wheel every time we write a program.
Yeah, exactly. Yep. All right. So if there's no more questions, yep. Thank you, King. All right. If there's no more questions, I will be ending the recording. All right.
Thank you, Jack. Enjoy your week.